Today I'd like to talk about the third of the three different methods for comparing alternatives that we're looking at in this course, which is the rate of return comparisons. Recall that we have looked at present worth comparisons and annual worth comparisons, which are very similar. In the first case, we're taking the cash flows associated with a project and taking it all to present worth and comparing the present worth of two or more projects to see which one's better. With annual worth, it's very similar, so we're taking everything to an annuity as opposed to a present worth. Rate of return comparisons are quite different in type. Here what we're doing is to essentially find an unknown interest rate associated with a project. For present worth and annual worth comparisons, we're given an interest rate, and we find the equivalent present worth or annuity. In rate of return comparisons, we don't assume a priori a particular interest rate. We calculate the interest rate that's implied by the cash flow itself. I'll show some examples of that in a second. But first I'd like to define a couple of terms. There are two terms associated with rate of return comparisons that are important. One is the internal rate of return. The internal rate of return is that unknown interest rate that's implied by a set of disbursements and receipts, or a cash flow. It's called the internal rate of return as opposed to an external rate of return, because it's internal to the project. There's nothing imposed on the outside at all. And we'll see later there is also an external rate of return to contrast with the internal rate of return. Now, if we calculate a project to have a particular interest rate associated with it, inherent in it, then that interest rate may be good or bad. But we have to compare it with something to determine whether it's good or bad, or desirable or undesirable. For example, if I have a project of sticking my money in the bank, and the bank pays 4% interest, well, I have to judge whether 4% interest is a good interest rate for me or not. And to judge it, I have to compare it to something. And what we compare it to is what's called the MARR, the minimum acceptable rate of return. And that's a desirable rate of return, what we'd like to achieve with an investment. So the 4% from the bank was less than my minimum acceptable rate of return of, say, 8%. Then I wouldn't invest my money in the bank. I'd invest it somewhere else. Let's give a more concrete example. Clem's considering to buy a tuxedo. Most of us don't need tuxedos, but Clem is the age where most of his friends are getting married, and he finds himself spending money on renting tuxedos for these weddings all too often. So he wants to assess whether it's worthwhile for him to invest in a tuxedo. The tuxedo he calculates will cost him $500, but it will save him $160 per year in rental charges over a 5-year life. And the question is, what's the internal rate of return for this investment? Well, what this is a simple unknown interest rate problem where we compare the disbursements and receipts. We have a disbursement here disbursement simply means paying out of $500. We have a receipt here, that's money coming in, which is savings of $160,000. We set them equal and see what interest rate results in that equality. We say that $500 disbursement is going to be equal to $160 over the 5-year life at some unknown interest rate. So, if you like, his investment of $500 is going to earn him interest. And we want to find out what that interest is. And so it's an unknown interest rate problem. We can solve it by saying that series present worth factor at some unknown interest rate is then going to be equal to 500 divided by 160, or 3.125%, or 3.125, I should say. And then from tables, we can see that series present worth factor at 15%, just by observation, is 3.3512, and at 20%, is 2.9906. We've bracketed the target amount at 3.125 by these two amounts. We can linearly interpolate between these two, as we've seen before. And we get an interest rate, we get I of 18.14%. So from Clem's point of view, he would look at different ways he can invest his money. He could invest in the bank at 4%. He might invest in bonds at 6%. He may have other ways of investing his money. But he would decide on a minimum acceptable rate of return for himself. Maybe it's 10%. And you compare that minimum acceptable rate of return to the 18.4% he earns from this investment. He's earning more. If he's earning more than his minimum acceptable rate of return, then this is a good investment. If he's earning less than his minimum, then it's not. So we need that MARR as well in order to decide. Now, another thing I want to do here is point out that there's another way of doing this calculation. The important thing is to equate the disbursements and receipts, but they don't necessarily need to be related as present worth, as I did up here. Here I related them, made them equal as a present worth. I could have done it differently and said that $500 can be considered to be equivalent to an annuity at some unknown interest rate, and that has to be equal to the $160 savings. This is exactly the equivalent principle, because we're equating the disbursements and receipts in a fair way, either both as present worth or both as annuities. And we could do the same unknown interest rate problem when it was 160 over 500, 0.32. Looking up in tables, linear interpolation, and you'll see that in your notes. However, the result I get gives me an interest rate of 18.01. Now I wanted to show the second way for a couple of reasons. One, to show there is a second way in that principle, but also point out that the answers are slightly different. We've got 18.14 up here, 18.01 down here. What this demonstrates is not that these approaches are different in nature. They are in fact the same. And if done with proper accuracy, we'll give exactly the same number. But we're linearly interpolating. And recall, linear interpolation is only an approximation, because the function may not be linear between the 2 points that we know. And that's what caused this distinction in value. But they're reasonably close. I just wanted to highlight that difference to help remind you that when we do a calculation using linear interpolation, the significance of the result is reduced. That we really can't go to four significant digits here. Probably only the first two is really appropriate. But of course, by and large, for most purposes, that's going to be enough. We're comparing whatever this value is to a minimum acceptable rate of return, which might even be 4 or 5 or even 10 integer values away in terms of interest rate. I want to do another example of an internal rate of return calculation, a little more complicated one. The Waterloo Baked Bean Company is looking at a new canner, and we're given a bunch of information about the costs and benefits associated with that canner. We've got a first cost of $120,000 with a scrap value after 10 years. We're given savings of $15,000 per year, increasing by $5,000 each year thereafter. So it's a gradient savings cash flow pattern there. And we've got some extra costs due to moving the more complex equipment, or to having the more complex equipment of $10,000 per year. So we've got a much more complicated set of cash flows here, involving both disbursements and receipts. The principle is the same, though, is that we want to equate the disbursements and receipts, either as a present worth or as an annuity, or as a future worth sometime. And we can do it in the way that's most convenient to us, because it's all equivalent. So what we want to do is choose the nature of the comparison that's easiest to calculate. Now we've got a present worth, we've got a future worth, we've got a gradient, and we've got some annual costs here. My judgment would be that doing it on an annual worth comparison basis would be the sensible way, because then we only need to convert the gradient to an annual worth rather than going through 2 steps with the gradient, for example. So we just need to sort of list these things out, and one at a time, and we get our equation to solve. So for example, we've got the $120,000 first cost. We'll make, say, cost negative. So that'll be a minus 120. That's money going out. We'll take that to an annuity over the 10-year life. At the unknown interest rate, which is what we're solving for, 10 years. So that's the first cost. We've got a scrap value. That scrap value is benefit, so it's positive, plus $5,000, taken to annuity from a future worth at the same unknown interest rate over the 10 years. Now we've got the gradient, which is savings, which is then positive, so it's plus the $15,000 base annuity plus the $5,000 gradient part. Now these are in standard annuity and gradient format, so don't need to make any changes there. So that's a gradient at some unknown interest rate over the 10 years. And the final component is the costs, so that's negative of $10,000 per year. And so that's all the costs and benefits. And since they're going to be set equal to one another, I can set that whole left-hand side equal to 0. I want to find where the costs and the interest rate, the costs and the benefits are equal. I could have equally well put the costs on one side of the equations, the benefits on the other, or I put them all on one side and set them equal to 0. I now have an equation that's pretty complicated. But if I solve it for I, that will give me my internal rate of return. So to solve it, well, I can start simplifying. For example, I can divide by $5,000 for one thing. I can combine this $15,000 and this $10,000 here. And I end up with this. I get minus 24. That's dividing the 120,000 by 5,000. And I get, that would just be the sinking fund factor, dividing it by 5,000. The 15 and the 10 makes just 5 divided by 5 is 1. And then that $5,000 disappears. I get the gradient conversion factor, and that's equal to 0. Now, this equation is certainly the most complicated one we've seen in this course for solving for an unknown interest rate. But the principle is the same. What we do is to choose an interest rate by trial and error, do this calculation, and find the closest interest rates we can such that one of them is above 0 and one of them is below 0. For example, at I equals 13, this whole equation turns out to give a value of 0.1474. And at I equals 14, this whole equation gives a value of minus 0.1004. So this one's just slightly above 0. This one's just slightly below 0. We've bracketed our target. We can linearly interpolate. Now, where this 13 and 14 came up, I came up with that was just from trial and error. Depending on the nature of the equation, you may find faster ways of doing it. But trial and error is often what you have to rely on. And it's not too difficult sometimes to come up with the closest convenient values. And then linear interpolating. The value you end up with is 13.6%. So that's the IRR, the internal rate of return, for this particular problem. It doesn't tell us by itself whether we should purchase this can or not. It depends on what else can be done with that money. If there's better projects that return higher internal rate of return, for example, this may not be the best. Exactly making that choice, deciding which project to do, is a little more complicated than it seems. We certainly want to compare it to the minimum acceptable rate of return, and if it's more than the minimum acceptable rate of return, we'll give it more consideration. If it's less, then not. But there are complications to that make it not quite so straightforward, which we'll deal with in a subsequent lecture. Thank you very much.